So I'm Sarthak Arne. I'm a third year student of IIT, and I'm the tech lead of ML and DS in GDSC IIIT-Bangalore. He's Naitik Singh Solanki. He's my batchmate. He's also a third year student of IIT. And today we are going to take the first session in ML study jams. I hope you guys are good. Okay, so firstly, I'm assuming here that many of you don't know what machine learning actually means and what goes into it. So according to you guys, what is machine learning? What do you think machine learning is? Anyone?
Raise your hand.
Based on some examples you already have, so if we check for certain situation, there is a certain result which is expected. So based on a large number of examples, we can then take a prediction.
Okay, so you're saying that machine learning is about making predictions, and we do that on basis of some data which we already have. Okay, so yeah, anyone else? That is a pretty good definition, and almost every time that's what happens in machine learning. Anyone has any other guesses?
Like first when we started programming, it's like we wrote the code and it will work for us. Like if we wanted to sort, we write the sorting code. But after that, like few things that humans could do, but the machines couldn't. Now we are trying to make the machine do the things which we could do and previously couldn't do. Like nowadays one might have heard that artificial intelligence making art. So first machines could not make art, but now they can. So one can say that's machine.
Yeah, that's a pretty good example, and that's what we are going to take as an analogy of machine learning. And we are going to see, like, when a child is born, we can say that his brain is not developed, and the baby does not know what's going on around his environment. So in the initial stages of their life, the baby, gauges about, takes information about their environment and tries to learn about what's going on in their environment. So that's what we will try to do with the machine learning models which we make. We give it some kind of a data which is analogous to the environment the baby is in, and then our model will try to learn things about the data or whatever it's trying to predict, and after that we'll make predictions which is analogous to a human being functioning in real life. So yeah, the next logical question is, how should we nurture our ML model? We said that similar to how a baby responds to their environment, we should also have some kind of a way so that our ML model can respond to the data which it is given. So yeah, so our main focus in this session will be about how to deal with data, because again, if you have a child, you want it to grow up and become a good person. Similarly, we want our model to be good, so we need to give it some good data. We need to process it nicely. So we have some good data, and we make a good model out of it. It shouldn't be like it should act a certain way in some conditions and in other ways in other conditions. And more or less, we want it to be accurate. That would be one of our goals while making a machine learning model. Yeah. Yeah. So a lot of machine learning is focused on data and data analysis, data visualization, and all of that stuff. You will have a lot of courses on the same, like related to data, especially data visualization. It's a pretty good course. You should take it. And you'll also learn data analysis and processing data in your machine learning course. But before that, we will give you some kind of an idea of how we do that. And like we have a child protection or kids mode in a lot of the apps we have nowadays. we also need to process and clean data before we can use it to train an ML model. And that will be the first step we take towards data processing, data analysis. And yeah, that's right. So yeah, I'll pass on the mic to Naitik, and he'll talk a bit about data analysis and processing.
Hello. Yeah. So, as Sarthak said that we have to clean the data. Now, why do you think we have to clean the data? It's data. What do we have to clean it? What do you think? Yeah. We have to structure it in some way so that it is useful to us, right? And that's basically the thing. So the data we collect are from some kind of surveys that we conduct or some kind of experiments that have been conducted in real life. And they aren't really feasible for an ML model directly. So we have to do some processing on them so that we can convert them into useful models. Alright, so now we'll discuss some techniques on how to do that. Alright, so here we are using a data set of some houses and features related to those houses. First, let me tell you that we are using a library named Pandas and some of the plotting libraries named Matplotlib and Seaborn. Some of you might be familiar with those, and if you are not, don't worry, you will learn it. Alright, so here we are storing our data in a data frame. So let me give you a brief introduction about what a data frame does. So you guys are aware of an Excel sheet, right? How it works. So there are rows and columns. So think of a data frame as a set of columns where each column represents a feature, and those rows, they will represent a single data point. So a single data point will have some values given for a particular feature. Got it? So that's what a data frame is, and we will be processing our data on the data frame. So yeah, you can look at it. This is how a data frame would look like. So these are some of the features for the houses like alley, street, lot shape, etc. Now comes our main step, data cleaning. So yeah, you can see here that there is a feature named pool variable and pool QC, right? Now, obviously not every house can have a pool, right? So there will be many houses which do not have a pool. So we won't have any data available for those. So what do we do, right? So we call them null values. Basically, we don't have any data for them, right? So if you have that, then yeah. So what we are doing here is corresponding to every feature, basically corresponding to every column, we are calculating the number of null values which we have, right? So here we can see that given a data set of 1460 something, out of those 1453 data points do not have any data for pool QC, right? Similar for missed feature, alley, fence, etc. So you can see that that is pretty bad, right? So what do you think? What should we do? Do you have any idea what should we do? Yeah, exactly. So don't worry, they might have some experience. Yeah, so it is generally said that if more than 15% of the data is unavailable to us for a given feature, then we just drop the column because it's basically like a lot of data is not available, so we won't be able to do much, right? So also this 15% is not a hard and fast value, like you have to think about it from a data set. But here we are using 15%, and from the data point, we have judged that any values which are more than 81, any missing values more than 81 will be dropped. So you can see that 1, 2, 3, 4, 5 and 6. We have 6 features which have a lot of unavailable data. So we just drop them, right? Any questions still here? Now, there will be some cases where only a few amount of data is unavailable, and dropping the entire column is not really feasible for us. So in those cases, we just drop the data point, right? So these are the two ways in which we deal with null values. Any problem with null values or dealing with them?
Can we fill in mean and median methods?
Yeah. So another way, another way of dealing with the data points, like for the feature we cannot do that, right? But if we have some data points and there is null, so either we drop them or we can, there are three cases we can do. Either fill in the mean, mode, or median. Again, that will depend on the data you have. That you have to fill mean or mode or median. Like if you have a shoe data, then median would be a better fit, right? But if you have like it's some categorical data where a lot of zeros are there and like 90 zeros and 10 ones, then putting a value of 0 would be more appropriate, right? So you can do that accordingly. Okay, now there can be some cases where you have duplicated values, like two rows are entirely same. So it's trivial, like drop them. We don't need two same points. Okay. Yeah. So what is our target variable? We have a data set. Now we have to make some prediction from the data set, right? So the prediction that we are getting, that is what we call our target variable, right? So that is what we want to find out, and other are the features that are affecting the target variable. So in our case, we have the house data set, and we are considering the sale price of the house as our target data set. So yeah, there is a function, a method in pandas which you can use for a particular feature. You can use .describe, which will give you the information about that particular feature. It's count, mean, standard deviation, minimum value, maximum value, and all. You can check that out. Also, yeah, so here we have the sale price. Do you guys have idea about normal distributions or distribution in general? You don't. Alright. So
okay, so we'll be discussing a bit about what a normal distribution is. How many of you have heard about a normal distribution, a Gaussian distribution, or something like that? I guess.
bell curve.
Yeah, bell curve. Bell curve is nobody a bell curve in a normal distribution.
This shape.
Yeah, it's basically this shape. Then you get some distribution like this.
Can I add?
Yeah.
So you are, especially I think MTechs pretty much know what a normal distribution is. So the IMTech was a junior, right? In J, have you had the thermodynamics, the black body radiation curve?
Yeah.
That technically follows a normal distribution. So like, see there you have observed it for a physical phenomenon, right? So in that situation, it can be generalized to other physical phenomena as well as you see the data also when they will explain. So that kind of a distribution looks like a normal distribution, which they will tell you what the parameters are. So just now related to that till they fill in your head with the proper parameters.
Okay, so this is what a normal distribution looks like. On the x-axis we have the random variable, and on the y-axis we have the probability distribution function for that particular random variable. So what do I mean by a probability distribution function? So if you take a value, say x naught, the corresponding value on the y coordinate will be the probability of that particular value for that random variable. Do you understand? So what do you think this distribution will signify? Any you might you know what mean is, right? The average of the data. So it will lie somewhere around here. So if we denote it by mu, this will be the mean of this whole distribution. And what this distribution function signifies is that most of the majority of the members we have will lie around this mean. You can see that if we have some value closer to the mean, say x1, the probability corresponding to that will be higher than the probability corresponding to this x0. That much is clear? So basically, if we have some value around this x1, the probability of finding that will be greater than probability of finding x0. That much is signified by this normal distribution. I won't show you the formula for this distribution. It might scare you. You will learn it pretty soon in our Maths 3 course. But yeah, so this is a probability distribution function. But sometimes in our data we have some skews or some defects in this data, and Rajat will continue talking about it.
Also, in the meantime, I'll just tell you how close the data is. So, do you know standard deviation? Do you know the term? So, from the mean, if you go 3 standard deviation from to the left and 3 standard deviation to the right, so the difference, this 3 standard deviation contains 99% of the data. That's how good distribution this is. If you are considering an ideal normal distribution. Yeah, okay. Coming back. So let me tell you what a skew is. You saw what a normal distribution is, right? So there's a mean and everything lies 50% of like how the data will be to the left, to the right, right? Looking at this, do you think that this is some sort of normal distribution, or it can be made in some sort of normal distribution? It looks some kind like it's more towards the left, right? So for this, what you say is that it's a right skew because a lot of data, random data is scattered towards the right. Alright. So these type of curves are called right skewed data. And so there are some terminologies which you can read here. I won't go into deep, but yeah, you have some value for the skew and all. There's a numerical value, but let's skip the maths for now. Also, we'll come back to this. Alright, I'll come back to removing the skew thing in a bit, but first let's discuss this. So, we saw that there were some features, right? So, how the features are related to a target column, we see here that GR live area is like versus sales price. So, you can see that we can see some trend, right? It's going like this. Right. Similarly, okay, and closed ports. So looking at this data, we cannot really say anything, right? So that's what we're going to deal in a bit. Also, this is one of the ways in which you deal with categorical data. What you see here are box plots, and I will explain them, and I'll come back to this in a while. But yeah, one thing you can see is that as the values increase, you can see some trend of increasing, right? Yeah. So these are basically how you have to plot the plots and you have to see the trends. But what we actually do with them, we're going to discuss now. So you saw that there were a lot of features, right? So we cannot actually choose all the features because there are 1,000 features and you cannot really choose those to calculate things. So to do this, we first Okay. This ugly looking diagram. This is what you call a correlation map, heat map. And do you guys know about covariance?
So yeah, what do you mean by covariance? So now you see here there are many features. All the features are listed on the y-axis and also on the x-axis. So you can see that what each cell in this plot, this heat map, conveys is that how one of the features is related to the other feature. So for example, every feature is completely related to itself, right? So you can see that this diagram is completely white because all the features are completely related to themselves. So the covariance or the correlation will be 1. But the other features, like the other cells, show some kind of relation on each other. So if you pick any one feature from this axis and other feature from this axis, you can locate their cell, and according to their color, you can check approximately what their covariance is. So what this map does is that it gives you a basic idea of how the features are related to one another. A great thing this heat map also conveys is that we can see one of the columns which we have in our data set is also the value which we are going to predict, right? So like the sale price is part of the table, so because it's in our training data. You guys understand? Yeah. So so that's why sale price will also be in you can see this. Sale price is also there in this heat map, and this row actually shows us how each of the features are related to sales price. And using that knowledge, we can choose which feature we have to use so that we get a good plot, or we can make a good prediction without wasting much of our system resources. Yeah. So as I said, clearly the above heat map was pretty difficult to untangle. So what we did was we took the correlation matrix, we took the row which I told you about, the sales price row, and we took the 5 most 5 features which are most correlated to sales price, and we plot them here. So this is now pretty easy to understand, right? You can see here how the top row is for sales price, and you can see how sales price is related to completely correlated to itself, and see overall quality, GR live area, garage cars and garage area are related how they are related to sales price. So the heat map gives you a good idea, and if you try to narrow it down to some features, some particular number of features you want, you can try to make a better prediction, and you can make a better choice on what features you want to choose to model your data. Okay, I'll pass it on.
Alright, so I hope you understood what correlation and why we chose these 5 features, right? So after selecting those features, now we will check for individual feature what are the kind of distributions. I talked about skew removals, right? So here we are really talking about if there is some skew, then we have to remove it and make it look like a normal distribution. So let's see that. Also, this will be shared with you. These are some of the terminologies which you can look after. Yeah, I'll talk about them, don't worry. So yeah, look at this graph. This is what I showed you earlier. So this is the sales price graph, and its distribution. So you see the black line, right? Ideally it should have looked like this, but it does not. So here I told you that this is a right skewed data, and to deal with right skewed data, we have a method to solve them. We log the data points. We do the logarithm of each data points, and then what happens after that is our data is now almost looking like a normal distribution. You can see that, right? The black line is the ideal normal distribution, and the blue line is what we are getting. Right. So again, GR live area also has a right skewed data, which will be solved by taking the logarithm. We don't have a left skewed data here, but if you have a left skewed data, you exponentiate it, and you will get the similar results. So, do you have any doubts here now? Yeah.
Like earlier you said that we picked the 5 highly correlated features.
Yeah.
Okay. So what if the 2 features in those 5 highly correlated features are highly correlated with each other?
Okay.
So do we have liberty to drop one of them?
Yeah. So in that case, if 2 features are highly correlated to each other, then we pick the feature which is more correlated to our feature and drop the one which is not that much correlated to our feature. We do that. So, alright. Let me go back there. Yeah. You can see this. So, in our sales price, we can see that overall quality is like pretty much correlated with all these. Not highly, but it is correlated. So one of the terms we use is if it is more than 0.85, the correlation is more than 0.85, then we usually drop them. Here we don't have that, but in case, let's say, if this one was more correlated, then we would have dropped this column. Right? So yeah, you can do that. Okay, so did you guys understand or should I explain it? Let me tell you that what he was saying is that 2 features are highly correlated with each other. Basically, what they are doing is they are doing the same trend to our target feature. Let's say there is a something like y equals to x and y equals to x plus 5. Right. So if I have target variable, then both of these values will more or less affect in a similar manner to my target feature, right? So I don't really have to keep both of these with me. I can rather drop x plus 5 or something. So that's what he was saying. Any more doubts? Alright, let's move to the next topic. Alright, so now we have something called normalization and standardization. So looking at our data, we can see that there will be some kind of data where we have, let's say, the area of the house. That will be like 1000 or like of the order 10 to the power 3, 10 to the power 4, right? In some unit, let's say. And there can be number of swimming pools, let's say. That will be 0, 1, 2. So they are not actually of the same magnitude or of the same order. So in that case, if we try to model them, we will have a so there is a term called weights. Satya will talk about them, but keep that in mind. So if we have features of very different orders, then our weights will be like some weights will be very high and some will be very low. So that affects our model highly, and in order to avoid that, we do something called normalization and standardization. So let me tell you. Yeah. So let's see. Yeah. So look at this. The garage area. It's like 500,000 of this order, right? But you can see this. This is 1, 2, 3, 4, and 11, 12, 13. So this one is like not of the same order as they are. Right? So in this case, we have to bring them to some similar order. So in order to do that, we standardize all the data, and yeah, this is what happens after standardization. You can see that all of them are of the similar magnitude, right? So in our case, we have done standardization. There is another thing called normalization, which basically does the same thing. again, which one to choose will depend upon the data that you have. So, yeah, I mean, you have to try both and see which one fits better.
Okay, so that was it from the point of view of standardization and normalization. So up to this point, we have processed a lot. Like the data has been processed a lot. The first step we took was cleaning the data. We got rid of all the missing values. So now we had our data which did not have any missing values, and all of the cells were filled with some values. We took many steps to do that. We removed our features, which are basically the columns, and we also tried to remove the rows, which are the data points. After that, we took many of the steps. We saw how our target variable looked like, the sales price. We saw how it was like a normal distribution. So that was, by these graphs, by these techniques, by visualization, you can see how your data behaves. You can draw out many conclusions regarding that, and that is what really data analysis is. And so after looking at data, like if you work on many projects, or if you try to analyze data a lot, if you do that a lot of times, you will have some kind of an intuition. Like we said that if the number of missing values were more than 15%, you should drop the column. We did not just think of that number. We tried to solve a few problems. We saw that 15% was more or less a good number to set our boundaries on, and now we try to act on that number. After that, you saw how we removed skews. We saw how taking a log on all of the values remove the left skew. The right skew. He also told you how taking exponentiation removes the left skew. So again, these are not the only ways to do stuff. These are most commonly used, but these are just one of the way to do things. There are a lot many different ways to do things. You can process your data in different orders. It's not necessary that you follow this particular order. You can try things out on your own. We'll give you out this Python notebook. We'll also try to tell you how to set it up and use it. But yeah, so now we are at a point where we have standardized and normalized our data. Now we'll talk about outliers. So what are outliers? Outliers are basically the points in our data which are not really near the distribution. Like you can see over here, if you look at this graph, you can see how these points are not very near to these points. You can see how these might be related to each other, but you can see how this kind of creates a disturbance in our prediction. So you generally don't want these kind of values that may disturb your prediction. These might skew. We'll talk about this more when I tell you guys about linear regression. But especially in linear regression, these kind of data can skew your final model a lot, and that obviously is not what we want. So we need some kind of a way to deal with these outliers. And first of all, we need to mathematically define what outliers are. So what we do is, so you guys know about, first of all, now we have our data, we have our 5 columns, our target variable, and all of the features which it depends on. You understand this, right? So now this graph, this structure that you see is called a box plot. And if you see any points which are away from the box plot, those are the outliers. They can be the lower outliers, as you can see in sales price. They can be upper outliers, like you see in garage area, or even in this. You can see it up. So how do we define? How do we define these boundaries? I'll tell you guys that. So this line you see, the midpoint of the box plot is our 50% median, or the median which we all know and love. And then this is the 25 percentile median, which is basically the 25% value which you have. So the midpoint median is basically the middle value that you have, right? So that is the 50% median. So similarly, this is the 25% and the 75% median. Is that clear? So now we have this area. Yeah, okay. So this is also called the lower quartile. The quart comes from the 25%, and that's why it's called the lower quartile, and this is called the upper quartile. Okay, these are just terminologies. The region between these two is called the interquartile region, which is basically the 75% median minus the 25% median. Okay, so now to get this, also known as the upper whisker, and this called the lower whisker, what you do is you add 3 times the interquartile region to the 75% median, and similarly subtract 3 times the interquartile region from the 25% median. So after all this maths jargon, what we have is a nice looking box plot, a box with 2 whiskers on either of its end. So lucky for you guys, you don't have to do any of this stuff. Seaborn will do it for you. You just have to call a function, and then you'll have this plot. And if you see some kind of points which are outside this box structure, then you know that you have some outliers. Do you guys have any doubts right now regarding outliers? No? Okay. So now the next step is how to remove. Yeah, okay, so one thing, you see I've made this class called outlier removal. When you guys will start coding, you'll see that making classes, even for small stuff like this, will be pretty helpful, especially because you might, especially during data analysis and creating models, it is recommended that you guys use classes. As you can see, the class outlier removal has 2 attributes called the lower and the upper quartile, which we can very flexibly use after this and create the attributes lower and the upper whisker. And now this is the outlier method, which basically what it does is if we have any values outside of this upper or lower whiskers, it maps that value to the upper whisker. See, if we have some kind of a upper outlier, it will change that value. It will doctor the data set and will change that value to become the upper whisker. Similarly, that will happen for the lower whisker. Are you guys clear? That's what this method is doing. And now we just call this method for all of the columns in our data frame. That's what we have done. And after that, we have this clean looking graph with no outliers. Fine? Anyone? Okay? Yeah. Yeah, okay, so one small correction. This line is the mean and not the 50% median. Yeah, I wanted to correct something. Now we come to the main model of today, the machine learning model, or something that, like Vidish said, will help us predict our target variable, which we have been talking about for such a long time, the sales price. So that the model which we will discuss today is linear regression. Linear regression, yeah, and particularly univariate linear regression, which basically means that we'll be using only one of these features to try and predict the value of our target variable. So univariate is for uni and variable, one feature. So that's univariate linear regression. So now we'll pause here for a while and we'll talk about how machine learning actually works. Like in practice, how do you go about machine learning? So basically in machine learning, first of all, you are trying to solve some problem, right? As he said, we are trying to predict some value. We are trying to see how a model reacts to the inputs given to it. But so mathematically, if you try to call it, we give some kind of an input to the model. It processes the input and gives an output, which is its prediction. That's clear? So can we treat it as a function? We give it some kind of inputs and we get an output. That's fine? Yeah, so this part is called the inference part of the model. We basically give some kind of inputs to the model which and it outputs a variable, the target variable. That's the inference part of the algorithm. Then we have the training algorithm. What the training algorithm does is it accepts the training data, there are two paradigms of machine learning, supervised and unsupervised. We'll not focus on that. We'll take it for granted that we have some kind of features and we have a target or a label for that. We basically, like we saw here, we have many features for the sales price, and the target is the sales price. So we input all of these values that you saw here, about 1,400 odd values. We input that to our model. It learns, it tries to learn how this data behaves, and it outputs some parameters. As he talked about, we call them weights. So what are weights? Weights are, models can be basically boiled down to weighted addition of many different things. So if you give it 3 inputs, it will give each of 3 inputs some kind of weights, and then will output the weighted addition. If you try to remove all the fluff around that algorithm, you will just get weighted addition of all the inputs. So what our model does is it tries to predict these weights. And in linear regression, what happens is linear regression is basically we get some kind of a data and we try to fit a line into that. That's why it's called linear regression. It will have some kind of, we'll talk about how to select a model, but for now we just know about linear regression. So what we'll have is a data which kind of looks like a line, which you saw earlier. There was this scatter plot of data which could be centered around the line. Yeah, cool. So that's what the data we have, and we try to fit a line into that data we have. Okay. So now, what do you think? What are the weights that we'll require for that line? Any guesses? Like it's simple coordinate geometry.
Slope and intercept.
Yeah. So slope and intercept, these two for univariate linear regression when we are trying to fit a line. For univariate linear regression, we'll have 2 weights, the slope and the intercept. If we have that, we'll have our answer. So that's what we're trying to predict in our model, the linear regression model. So yeah, we come back to that learning algorithm. So now we have our data, but we can't just put all of the data into training and see what comes out, right? We also need some kind of metrics to see how good our model is. We, in case of linear regression, we use the metric of mean squared error. Mean squared error. So error is basically some kind of difference between the output variable and the predicted variable. Squared is squaring the error, and mean is taking the mean of all the predictions. Fine? Mean squared error. That's the metric we generate. There are many other metrics, but for now we'll just consider this one metric which we will try to judge our model on. So what we do is we need to separate out the training and testing data. Why do we do that? Do you guys have any clue regarding that? Yeah. Any clues? Why do we try to, if we have all of our data, why do we try to separate it out into training and testing data?
If we are training the model on the testing data as well, and then taking the testing data from the training data, we are just taking from the same distribution and applying the training, so it does not really infer.
Yeah. So if we take an analogy of a real world, what if your professor gives you all the exam questions during your class? That does not make sense, right? You need different questions for the classroom and different questions for a test. that's basically what we're doing when we're separating the training and testing data. What we are trying to do is we train our model on different data, and we give the testing data follows a similar distribution, but we are just trying to check if our model is trying to mug up all the data. It really does not happen that often with linear regression, but it will be very common as we move on to other more complicated models. So, and that's what we call is overfitting. Overfitting is basically when your model just mugs up all the training data, and when you give some testing data, it just cannot process it. So so that's why we need different training and testing data. And similarly here, before training our model, we will separate our data into training and testing, and that's called train test split. And scikit-learn, the module, the library which we'll be using, helps makes all of this very easy. First of all, what we'll do is again one thing, before splitting our data, we usually take a random sample out of it, like we randomize all the the rows, and after that we try to split our data. Any guesses why we do that? Why do we first randomize the rows, and after that we split into training and testing? Yeah, that's very possible. As Ranjit mentioned earlier, a lot of times the data which we receive are from some kind of a research, or they are generated somehow, or the sources might not it's not for the sources for us to give good clean data. So as Girish said, we need to separate out the data if it is similar. Say if I and 5 of my friends go to a survey and give them answer their questions. If I and my 4 other friends are alike, all of our data will be pretty nearby and will be pretty similar. So if someone tries to predict on that, all of our data will be together in either of the training or the testing split. So that's why we try to randomize our data. So if the rows are similar, we try to separate them out. Is that clear? Why we randomize our data before the training and testing split. Yeah. Okay. So over here, frac equal to 1 is basically it takes the whole data, but this sample function, what it does is it randomizes it shuffles the data frame, df train, and it shuffles the data frame, and after that we make a copy out of it. And random state is just a random state that we do. It's kind of a seed for randomizing the randomizing part. Right? So after that, as this is the as we are talking about univariate linear regression, we'll take our label and only one of the features. We are considering GR living area right now, frankly because it was easier to plot and demonstrate. Yeah. Because there are 80 other columns, and it's very difficult to show all of that. So we took the simplest one, GR living area, and we are going to demonstrate how linear regression works in the case of univariate linear regression using one of the features, GR living area, and the target sales price. Fine. You can see this. Okay. So this function df.head, what it basically does is by default it gives the first 5 rows of the data set. You can pass any odd number in that function, and it will display that many first. Say if you put dot head into bracket 10, it will show 10 first values from the data. So yeah, that's basically what that function does, and it's pretty helpful to see if you are going like all of the things are going nicely or not. Now we introduce you to your, I guess, third friend of ours. First was pandas, then scikit-learn, and now NumPy. Now NumPy is very powerful, and you can do all of this. I'll show you what we are going through to plot all of this using scikit-learn. But NumPy, being NumPy, has a function called polyfit which could do all of this in just one function. So basically NumPy is very powerful, and it helps you treat your data like you would do it mathematically. Like you can write any matrix, linear algebra, function or equation expression on a notebook, and you can copy that as it is to NumPy, and it will give you the expected results. And clearly, it's very nice. And people say that Python, and that they are correct. Python is very slow, but what NumPy does is it uses C++ subroutines inside that, and C++ being a fast language processes the data better than Python lists or whatever. So you might argue that Python lists are better because they can handle various objects, but usually in data analysis, machine learning, we have a feature will have same kind of data, right? It won't have different kinds of data in one single feature. So NumPy arrays, NumPy handles things in arrays, and NumPy arrays makes it make things very easy and fast for us because NumPy uses C++ underneath. So we convert all of our data frame into NumPy. Now you can see the first column over here is sale price, and the second is the feature or GR living area. So you can see when we convert it to NumPy, it gives us an array, and it outputs the same as it was there before in the data frame. Yeah, and this 2NumPy is a function of pandas data frame. Yeah, okay, so we split our data into the label vector and the feature vector in that step over there. It's called the horizontal split, and afterwards we do this train test split. Now the train test split is included in scikit-learn, and what it basically does is you need to give it an input. Currently we have the train size equal to 0.7. So what it will do is it will allot 70% of its data for the training data, and the 30% of which is left is given to the testing data. So yeah, that's what this attribute does. And again, random state is the train test split itself shuffles the data. So we gave it another seed so that all of our results are consistent all over. And now we input the label and the feature vector, which is basically the x and the y, and we receive as output train x, test x, y train and y test, which are pretty self-explanatory. Now, yeah, this is the how simple it is to train your data in scikit-learn. So it's basically, you can see I initialize the model over here, linear regression, and then I asked it to fit x train and y train. That's it. When I execute that, it will do all of that linear regression stuff, which I will explain in some time. And after that, you will have some kind of this. So the blue is clearly the data which we had. Here is the generating area, that's the sale price, and this is the predicted line which scikit-learn predicted it out for us. Everything clear right now? Fine. Scikit-learn, what scikit-learn is basically does is it tries to find those weights which we talked about, the slope and the intercept, and it outputs them, and using that we can plot out a line which is this red line. Now again, as I talked about, this is done on the training data. As you can see, I have plot it using the trained data, but we also need to see how it does on the testing data, right? Because that's the main test. It only matters how well you score in the exams, because the classroom stuff does not really matter, unfortunately. And this is how things happen in the testing world. So this is the testing data, and that's the line which we saw earlier. But this is all visual, right? We need some kind of method. As I talked about the mean squared error, we need to calculate that for the training data and our testing data to see how that goes. So again, scikit-learn comes to our rescue. It gives us this, one second. Yeah, this mean squared error. Mean squared error is again from scikit-learn. We provided the y train and we provide the predicted values, and it gives us a training error of 0.435. And when we try to do it on testing this is not always the case. This is the case over here, and you can again take another analogy with your exams. No matter how you do on the practice questions, there is still a chance that you might mess up during your exam. So that's what is shown here. So there's testing error of 0.48. Yeah, again. So as I told you earlier, this model is very simple. Like a simple thing, like a complicated thing like sales price of a house cannot be really predicted with just one feature of it. Like you can just say that this is the square footage. You also need to see, like if you say I want 3,000 square foot house, but it's on the moon, no one's gonna buy it because you need all the other the other features kind of give it a context, and the final variable or like the target variable also depends on these other features, and we need to capture that. So this was the very basic case of univariate linear regression, and you can extend it further using multivariate linear regression. But multivariate linear regression is difficult to see because it requires 3D plots and all of that stuff. And yeah, so that's how we do it. Like this was basically a demo for linear regression and data analysis. But what is linear regression? We treated it like a black box over here. I gave you a brief overview, but we did not really talk about what linear regression was. So now we'll talk about what exactly is linear regression. So as you saw, the more visual and the better answer would be fitting a line to our data. But that's not how simple our world is. We also need to deal with this. This is our final answer, and that theta is very scary. So, yeah. 1 second. So what exactly is linear regression? In the next few minutes, we'll try to use this. I purposefully put this equation to scare you guys. Now we'll move on to simpler, not simpler, but yeah. So behind every ML algorithm, almost every ML algorithm, there is this notion of a loss function. Once you get this loss function, going the final step is very easy. After you get this loss function, you just need to minimize or maximize this loss function to get the final predictions, or reach the final point where you can say yeah, now my model is ready and now I can use it to predict stuff. So any guesses on what this means? A hint: this is a matrix, this is a matrix, and this is a vector. Well, any guesses? What?
Summation of data.
Yeah, exactly. So as I told you, we use mean squared error as a metric for how good our linear regression model behaves. We actually also use it as a loss function. I'll tell you how this stuff comes from mean squared error, and just a notation. J theta represents the loss function, and again, yeah, the theta, I forgot to tell you where to attack. Theta is what our model is trying to predict. Theta are the parameters of our model, and if you think about it, if our model is trying to predict the theta, it should also be a function of theta, right? Because the loss function is basically what defines our model, or what gives shape to our model. So theta should be the input to that loss function. Now, see, now what happens? This was a plot that you saw earlier. So what linear regression basically does is, it takes each of the data points. Say we take this data point, we take this data point, we try to minimize this distance. Can you guys see? You guys understand? We try to minimize this distance. So what is this distance? It is square of this distance actually. We try to minimize the square of this distance. This is the y, the output value, and this is the predicted value. And what happens is, at the beginning of, before we try to train our model, we randomly initialize the line, and it can go squared of the vertical distances between the predicted value and the given value. You guys get it? Now, it's pretty intuitive if you think about it. If that line was say here, would that be the choice for minimum vertical distance squared, or is this the better choice? This is the better choice, right? So from this notion, we try to get back to that scary expression that you saw earlier. So now the next step, again, we'll go step by step. So theta 1 is basically our so I'll tell you guys what x is. X again is a vector. You can x has two values. I told you guys that we are doing univariate linear regression, but to make things easy, we introduce one more column in our data set, which basically is filled with ones. And we do that because when we multiply that vector with our weight vector, it basically gives back theta naught. X1 doesn't really matter and it isn't changing, right? Do you guys understand? Did I complicate things a bit? Yeah, I'll tell you. Yeah. So theta, as you saw, is theta 1 and theta naught. Our line's equation generally is y equal to mx plus c. Agreed? Now we just rewrite as y equal to theta 1 x. I'll tell you what this superscript means. It might be pretty clear. And then theta naught into x 0. Similar equations. Agreed? Yeah. What we then do is, suppose we have our data set like this, right? We have, this is the sale price, and this is that GR something, I forgot what it was. So this is the x1. What we do is we introduce another variable which is just filled with ones. So now what do you think will happen when we try to multiply this row vector with this column vector? Will we get back that? Yeah, fine. So that's why we introduce this x superscript 0 and we put it as ones, because we want x to be included somehow in this vector notation, because frankly, as I told you, vectors can be written as it is into numpy code, and numpy makes things easier. Okay, agreed? Why doing this is a good idea. Fine. I'll get back to the slides. Yeah. So that's what I have wrote here. See, this is the vertical distance between, say, this point. It can be negative. This point and another point. This corresponding value will have two values of x, right? X1, xi1 and xi0. Fine. Agreed. And when we multiply it with this column vector, the theta, the weights, we will get some kind of a prediction value. You can look at it this way. We are basically trying to find the vertical distance, right? So what we do is we take this value and we'll subtract this value from it. Fine. So this is the y which we have from the data, which is the ground truth value as we call it. This is that, and we are trying to find the distance from our predicted values. Okay, this is what I have written over here. Fine. This is what our model predicted. This was the equation of the line, which is basically this, and we subtract it from this. Fine. Everyone clear? Yeah. Okay. So we'll divert a bit and we'll talk about convention. So as you saw earlier, we have many data points over here, right? So by convention we talk about n data points, which which is basically the number of rows you have in your data set. Fine. And then we have xi1, xi0, and then y. I think then this might be pretty self-explanatory. For the ith row, this is the first feature, this is the second feature, and this is the target. Fine, that is our convention. And for a univariate linear regression case, this is what we have. But in case where we have a lot of features, this can extend towards the left, and we'll have x0, x1, x2, and so on. And sometimes, yeah, it's scary, but we can also have two target variables, and we'll again follow this convention for these target variables. So yeah, everyone clear about the convention? Any doubts? I don't think there are any. So I'll move forward. So we are trying to make it easier to read. All of these symbols, the conventions, it can make stuff easier to read, difficult to read, I mean. So what we do is look at that equation, and then you can look at this equation. Which do you think is easier to read? The first one or the second one? This one or this one? Second one, right? This has stuff written in vector notation. This is a scalar, that's the sales price. This is, I'll tell you why I wrote x transpose. So this is a row vector and this is a column vector. So by convention, if we talk about a vector, a normal vector, when I just say vector, I talk about a column vector written like this. So you can see this is a column vector, and again theta is a vector, so it is also a column vector. And what we are doing is we take a transpose and we multiply it with theta. We take a dot product of with theta, and as you saw earlier, it will give us back this equation. Fine, all of this is clear. And why we do that is, if you look closely, if we take a transpose of x, we will get back this. You can see how in our data set x is always written as a row vector, right? So that's why we take the convention, as our convention says that when we call a vector, it is a column vector. So we take xi as this and we write xi transpose into theta. Fine. So as this is easier to read, we use this notation, and again NumPy makes stuff easier to calculate when we write it in vector notations. Okay, yeah. So now you see this. Do you agree? This is that equation which we had earlier. This is the predicted value of y from our model. Agreed? This is the x row vector, and this is theta, which we multiply and get the predicted value. Everyone fine? So what we do is we will sum all of that squared error from 1 to n. That is our loss function. Everyone see how we got from the vertical distance, which is basically this, which you also call the error, because it is the difference between our predicted value and the the ground truth value which we had. So that's what we call an error. We square it and we add it over all the data points. So that is our loss function. And now we go from that to here. How do we do that? Again, scary stuff. So what we do is we have this form. Right? Agreed? We have this form, right? So now what we do is, if you see x is the matrix. X is basically all the data set of all the features. Okay, so in our data set, if you remove the target column, what you will have is x, capital X. This is the matrix. Fine. So X will look like this. X x1, x0, and it will be a matrix like this. Fine. This is what we have, X, and this is Y. This is basically the collection of all the yi. Fine. So now what happens when we try to multiply x with theta? If we multiply it with theta, we'll get theta 1 and theta naught. So what do you guys think will x theta be? Come on guys, you just had a linear algebra course. So what will x theta be? Yeah. Can you speak a bit louder? Yeah, exactly. So, yeah, predicted by. So what we'll have is we'll multiply this row vector with this column vector and fill up the first cell. Then we'll have this row vector, again this column vector, we'll have the second cell. And this you guys can see is just XR transpose. Is it not? Yeah? Can you guys see how if we multiply x theta we get just a column vector of all the y predicted values. Fine? Clear? Should I explain it once more? Anyone? No? So what we'll have is what we call y hat. Y hat, it's basically all the set of all predicted values. X theta will have a set of row vectors. You multiply it with the column vector theta. Each of the column these vectors get multiplied, and it gives us a column vector of all the outputs, the predicted values. And now, what if we do y minus x theta? We have errors in each row of y minus x theta, because in y we have the ground truth values, and in x we have the corresponding predictions, x theta. Yeah, fine. Now our final goal was to sum up square these errors and then sum them up, right? And what's the easiest way to do that? Norm. So norm is basically there are many definitions. More specifically, we take the L2 norm. L2 norm is basically multiplying each cell of this vector with itself and then summing up all of them. So simply we can write it like this. Do you see how we get the square of all errors and then sum if we do that? If we have a vector, any vector, and we multiply it with itself, say we have a1, a2, a3, a4, similarly over here, what we get is basically, right, this is what we get if we do a column vector squared. Agreed? So if we do it with this, again this is a column vector, we get back this. Fine? Are you clear? We just square the sum and then add them. So this is what I have written. So this is the short way of writing the L2 norm, is y minus x theta squared. And we are back to our original loss function which I showed you guys. This is y minus x theta squared. So this finally is the loss function of univariate linear regression. Now we are not done with the loss function. So the loss function defines how we act and how we optimize our model. But the next step of doing that is a gradient. So as I told the loss function. And how do you minimize any function? You just take a gradient and equate it to 0. That's one of the methods, and that's what we'll do. And now vector differentiation is little dicey, so you just have to take my word for it. And what you get after differentiating this expression is this value. So this is the gradient for that particular loss function. And after we find the gradient, we equate